Good day, greetings, and welcome back to the Anti-Science Theory. So today, I want us to quickly just go through another topic under Grade 12 Physical Sciences, Paper 1, that is physics, and we will mainly focus on the work, energy, and power. Right? So it's quite a short. I mean, it's not short, and it's not long either. It's just an average amount of work in this topic. Does require a lot of logical thinking. It's quite a fun topic. But if there's some of you that actually struggle with this topic, at this point, my job is to make sure that I explain it in the best way that I can. Before we get into the video, please don't forget to do the right thing. Don't forget to like, to comment. Your comments make my heart warm and fuzzy. Your comments make me know what it is that you guys need, right? What it is that you guys are happy with, what it is that you're not happy with. You can't always be happy with everything. There's some things that you might want to be, or they might see that at least do this, and but yeah, just don't forget to like, comment, share, and with your friends, with your family, with your cousins. Although they are not in matric, they will eventually get to matric, and they'll definitely need this at some point. But for now, just want us to get into the crux of work, energy, and power, and let's hope that this will be one of the best lessons ever. Okay. Okay, so first things first, I want us to get the definitions out of the way, just very quickly. All right, so the first definition that I want us to look at is what we call the work done. Right? So this one, I'm not actually going to write down the definition. I'm just going to say it out, because I believe that, in fact, I always recommend that every definition that you need to know, you just need to make sure that you get those definitions from the exam guideline, because that's the one document that's always going to make sure that you totalize on those definitions, right? But in the most basic sense, when we speak of work done, it's typically just a product of the displacement, right? It's a product of the displacement and the component of the force that is parallel to the displacement, right? I repeat yet again, work done is basically defined as the product of the displacement and the component of a particular force that is parallel to that displacement. So the definite, or rather the equation that we work with for work done is simply just, so work done is equivalent to the force times the displacement, the parallel component of the displacement. So this is what we look at. This is the definition rather of work done. Okay, where in each case this is just gonna be your work done, right? Remember, this is work, so it should be measured in joules with a capital J, and then that there will be your force, the force that you're basically focusing on. So I'll just call that the force of focus. The force changes. It's not one type of force. I say it's the force of focus. Maybe you can be looking at, say, perhaps your gravitational force. You can be looking at your frictional force. You can be looking at it can be any kind of force. It isn't just one particular force all the time. And we all know by now that forces are measured in newtons. Okay, and then this right here would then be your displacement. Remember that displacement is indeed a vector, so it does require direction as well as magnitude. Right? Displacement is measured in meters, and then this right here is your angle theta. Is your angle, right? And this angle here, ladies and gentlemen, is an angle. I mean, it changes from time to. It's not. I mean, it is the angle that you know from mathematics, but we don't particularly use I mean, the only numbers that we'll be focusing on for the angle theta would be 0 degrees, would be 180 degrees, and would be 90 degrees, and would be 270 degrees. It all depends on the type of question you're looking at and the type of force that you're dealing with. We'll get deeper and deeper into what the angle theta basically entails and how you can use the angle theta in different scenarios. But for now, we'll look at the definition of work done. And as the definition says, it is the product of the displacement and the component of the force that's parallel to the displacement. Right. Um, just to quickly say, let me just add on to what theta is exactly. Just push this to the side a little bit. Um, just to be more precise, theta is typically just the angle that lies between, it's the angle between any kind of force, right? It's the angle between any kind of force and the displacement of a certain force. It's any kind of force between it's the angle between any force and the displacement vectors. So these differ depending on the type of question you're looking at. Like I've said already, it can really change from time to time. But we'll do a couple of exam questions in a few videos, and we'll see how that works. Okay. Just to add on to a few things that you must always remember. Just a few things that you must never forget, you know. So very helpful when you get to the exam. Okay, so for starters, now I'm gonna go into how the angle of theta changes from time to time. You know, how the angle of theta changes depending on the direction vector, depending on the type of force that you're looking at, you know, and well, how type of force relative to the displacement, right? So first and foremost, whenever the force, right, whenever the force that you're looking at, whatever force that you're looking at, and the particular displacement of a certain object, right? Whenever the force and the displacement of a certain object, just fix that. Whenever the force and the displacement of a certain object are in the same direction, right? Whenever they are in the same direction, right? Then something must happen. This is gonna affect the angle theta. So this is how it affects the angle theta, right? So whenever you have the force and the displacement all in the same direction, this is how it actually affects theta. So the angle of theta becomes um, 0 degrees, right? And as a result, when you substitute into the work equation, you'd see that this will basically be the cosine of 0 degrees, which then becomes a positive 1. Right, we then conclude that if you have a situation like this, then we say that particular force that you're focusing on does positive work. Right, that's what we basically say. So when your angle of theta is 0, then we're saying the force that you're looking at, the force that you're dealing with at that particular moment in time, is doing positive work. Sorry, it's just I think of something and I write something different. The force does positive work. That's what we say. Okay. Um, right. So a basic so if you pay attention to this diagram over here. So I have a diagram here. I have a 10 kg object, for example. Let's just make this let's make it 7. Right. The mass, not that the mass affects anything in this case. So what happens now is that let's say I take my object and I displace this object to the right, right? So let's say my object is being displaced to the right at some particular force applied. Um, that is unknown, of course. We don't really need to know the numerical values. You just need to understand the principles behind this. So I have a force applied, which is displacing my object from the left to the right. So this is where my object ended up. So this is my 7 kg object yet again, and this is where it was displaced to. So I use dashed lines so you can see that it moved from one place to another. Okay, so notice something. This force was displaced to the right. Ah, man, sorry. This object was displaced to the right at some particular displacement. Right, this would be the displacement delta x, right? But what do you notice? What you would notice is that my object is being displaced to the right, right? It's being displaced to the right, and my applied force is also in the right direction. So it's also in the direction to the right. So the direction of my force is to the right. So what do you notice, guys? The direction is to the right. The object is displaced to the right. So your conclusion would then be that the force applied and the displacement are in the same direction. Are in the same direction. They are in the same direction. And as a result, if they're in the same direction, we then conclude that force applied does positive work. It does what? Positive work. And since that's the case, it does positive work, right? And with that being said, the equation of work done will then be as follows. The equation will then be work done by the force applied, right? That's a subscript FA, is equivalent to the force applied magnitude times the displacement times the cosine of 0 degrees. Why are we using 0 degrees, ladies and gentlemen? Because we said that whenever an object does positive work, then the angle of theta then needs to be 0 degrees. Hence, our theta here is therefore 0 degrees because our force applied is doing positive work. Whenever an object is in the same direction as the displacement of that particular, sorry, if whenever an object is being has a force that's pulling it, or when there's a force acting on an object, and that particular force acts in the same direction as the displacement, then we conclude that the force and the displacement are in the same direction, and as a result, that particular force does positive work. And what you substitute for the value of theta is then your 0 degrees. I hope that was very clear. Okay. The second scenario would be when you have a different type of force. So let's say, we all know our big old opposition force. Whenever the force, right, is in the opposite direction. Whenever a force is in the opposite direction, whenever a force is in the opposite direction to the displacement, of a particular object, notice the keyword opposite. Whenever the force is in the opposite direction. In scenario number one, our keyword was in the same direction. So here the keyword is when the force is in the opposite direction to the displacement, then what do we conclude? We can then conclude, okay, from what we have here, this then changes the value of theta. That is, the value of theta then becomes 180 degrees, right? So whenever you have a situation whereby the value of theta, or rather a force acts in the opposite direction as the displacement, then you choose the value of theta to be 180 degrees. That's how it should be, ladies and gentlemen. And as a result, what you would substitute into your equation would then be the cosine of 180 degrees, and this should be equivalent to -1. So notice the sign there, it's negative. So what conclusion can you make? You then conclude that that particular force that you're looking at does negative work. So that force then does negative work. And that is why we choose the angle of theta to then be 180. Okay, right. So just a little diagram here again. So there it is, right there. There's my, say I have a 2 kg object here that is being displaced by some force F A to the right, right? And I have this. So this is where my object ended up. And then notice the displacement. My object was then displaced to the right. Right? My object was displaced to the right. Okay. Now, Notice something, guys. If I then say I have a friction a rough surface here, if I say that my surface is rough, what does that tell you? That tells you that we have what we call our old friend frictional force, right? So frictional force in this case is what we'll have. And frictional force would obviously act in the opposite direction to the displacement. So in this particular case, we all know that friction opposes the motion. So friction would then act in the direction to the left, right? It always acts in the opposite direction. So what can you conclude? Notice, right? Notice that in this case, your friction and the displacement are not in the same direction. They are not in the same direction. So they are not in the same direction. That's what you see here. That your friction as well as your delta x are not in the same direction. So what conclusion can you make? You can then conclude that friction does negative work. Remember, what did we say? We said that an object, or rather a force, does negative work whenever it is in the opposite direction to the displacement. Right, so that's what we're seeing here. We're seeing that the frictional force and the negative and the displacement are not, there's my keyword there, they are not in the same direction. And as a result, we conclude that the frictional force actually does negative work. Okay, and what is our value of theta in this case? So when we substitute into the equation, we'll then have the work done by friction will be equal to the value of the frictional force times the displacement of the object times the cosine of 180 degrees. That's what we have there. Okay, really hope that was clear, guys. If anything was not clear, then please do type there into the comments so I can then see where I maybe might have made a blunder. Um, but all in all, so far, I hope all is well. Okay. Then another scenario, very common, a less common scenario, but it's very important for you to know, is whenever you have a situation when the force that you're looking at is perpendicular. So you have a perpendicular force to the displacement. So whenever the force is perpendicular to the displacement, right? Whenever the force that you're focusing on is perpendicular to the displacement, what conclusion do you make, ladies and gentlemen? We then say the angle of theta is then going to be equal to to 90 degrees. We choose angle theta to be 90 degrees. And as a result, what happens to the cosine of theta? The cosine of theta then becomes 90 degrees, and as a result, that gives you 0. So consider an example yet again. So I have a flat surface right here, and I have my object that's being displaced to the right, right? That's the displacement of the object is being displaced to the right by some particular force, you know. So this is how it is. Now it has been displaced, right? This is my force has been displaced. So let's say this is 2 kg yet again, and then this is also, yeah, it's still the same mass. Now, we then say to you, say you have a force like normal force, right? Now, what you would notice is that normal force would then act perpendicular. By definition, it would act perpendicular to the surface, right? And then what do you notice? If you were to draw a vector diagram here, where you would have the displacement of the object to the right, and you would then have the normal force acting upwards, right? What you would notice is they form a 90-degree angle where they intersect, right? At the intersection point, there's a 90-degree angle that they form. Hence, we say that the angle of theta is then 90 degrees. They form a 90-degree angle at the point of intersection, right? It is the same approach here, ladies and gentlemen, that another reason why we say it's 180 is because if you were to draw your vector diagram here, you would have the displacement to the right, and you would then have your frictional force in the opposite direction, right? And then what do you notice about an angle, right? Let me just fix this line. What you would then notice, ladies and gentlemen, is that since this is frictional force, there is an angle here, which is angle theta, right? And what do you notice? These are angles on a straight line. And since these are angles on a straight line, we know by now from Euclid's geometry that angles on a straight line are supplementary and are equal to 180. That's what it means to be supplementary. Hence, we choose the angle of theta to be 180 degrees here, ladies and gentlemen. And in this case, when you have object, the force and the displacement in the same direction, if you were to have a vector, you know that your vector would be to the right. Please, by the way, it is not always to the right. It's just the situations that I have in this case are to the right. But in the exam, it might be a different case. It's just not even about understand. It's not even about the direction. It's about understanding the principles behind this whole thing. And if you say the displacement and the force are in the same direction, then you would have something like that with the force applied. But what do you notice? There is no angle theta between these two. Do not assume that there is just because I have my vectors, there's an angle there in between. No. It's a thing of saying I can't just put the vector for FA on top of the delta x because you wouldn't even see that there's a vector there. So we just make space between them so you can see that there are two different vectors, right, that are actually in the same direction. And what you would notice is that between these two vectors, there is no angle because it's a thing of saying FA is literally on top of delta x, but we don't put them on top of each other because we need, or rather we expect to see the different vectors, right? But in a logical reasoning way is that what you should realize is that FA and delta X are exactly on top of each other, but we do not draw them on top of each other because we need to see, for example, the marker needs to see that you have two separate vectors that are in the same direction. But in the most basic sense, there is no angle theta that acts between these two, right? So it's a thing of saying if my delta x is in that direction, then FA is also in that direction. And notice that FA lies on top of delta x. But we don't do this because we need to see that, or rather the marker needs to see that there are two different forces, right? Hence, we leave space in between. But this is how it actually looks like. And what you've noticed is that there is no angle theta between these two vectors here. There is no angle theta between FA and delta x. Hence, we say that theta is then equal to 0 degrees because there is no angle between those two vectors. But in this case, there is an angle between them that's 180 degrees. In this case, there is an angle between them, and that angle there is then 90 degrees. Hence, we choose theta to be 90 degrees. And as a result, what do you notice? The force and the displacement are perpendicular to each other. They are perpendicular to each other, right? And what can you conclude from this, ladies and gentlemen? Since they're perpendicular to each other, what you can conclude is that the angle of theta is 90 degrees. And since that's 90 degrees, when you write that onto your equation for work, you would then have something of this nature. Work done by normal force is then going to be equal to the magnitude of the normal force times the displacement times the cosine of 0 degrees. When you sub this into your calculator, you should get the work done by normal force equal to 0 joules. That is always the case, ladies and gentlemen. On a flat surface, your normal force as well as your Fg does 0 work. So even if you were to draw the component of the gravitational force, what you would notice is that gravitational force would also act perpendicular to the displacement. And as a result, the angle between the gravitational force and the displacement is also equivalent to 90 degrees. So The work done by normal force is always 0 degrees when the object is on a flat surface, and the work done by Fg is also always 0 degrees whenever you have an object on a flat surface. Okay, I really hope that was clear, guys. I really hope that was clear to you guys. If there were any questions, complaints, concerns, then you can post those into the comment section and I'll get back to you as soon as I can. Now, just to cover the last part of this video, I just want to talk about what we call um, the net work. All right. Remember when we did F net in Newton's laws, net means the sum of all the forces. So when you're saying net work, this is basically the sum. This is typically just the sum of all the work. It's the sum of the work done by different forces, right? It's the sum of the work done by different forces, basically. Okay, so the formula for net work is as follows. So W net is equivalent to the net force acting on an object times the change in position times the cosine of theta. This is the first equation that you have. The second equation you can use is that W net is equivalent to the work done by the first force plus the work done by the second force plus the work done by a certain force, right? So it depends on the number of forces that are acting on that particular object. Right, so these are the two forces that you have. These are the two equations that you have that basically refer to the network. Okay, right. So just a few things that I want you guys to keep in mind is that whenever you have work net greater than 0, then we say that energy, remember this means that it's positive, right? We say that energy is added to the system. Just keep this in mind. Energy is added to the system, right? And whenever you have the net work less than 0, that means it's negative, of course. That tells you that energy is actually, what do you think it is? If whenever W net is positive, that means energy is added. What do you think it means when W net is negative? Aha, the energy is removed, right, from the system. Removed from the system. Okay, so I just need you to make sure that you keep this with you, ladies and gentlemen. Do not lose this information. It's just very important. Um, you'll find different types of scenarios that really need you to remember this piece of information. Okay, so this is what we have thus far, and I think we'll just call it a video on this one. And in the next video, we'll then look at more in-depth understanding of work energy and power. We will look at the work energy theorem, conservative forces, non-conservative forces, and everything in between. But from me to you, ladies and gentlemen, I hope everything so far was clear, and we'll meet in the next video. Goodbye.